Hello everyone, thanks for coming. My name is Yiwen. I'm a data scientist at Microsoft Gray System Lab. So today I would like to introduce you the project KEA, Tuning an Exabyte Scale Data Infrastructure. It is a collaboration between multiple teams at Microsoft, including the GSL, the Gray System Lab, the Cosmos Engineering team, and also the Cosmos PM team. So the goal of today is we would like to introduce you a data-driven system to automatically tune the various configuration parameters at the cluster level. And we will present a set of examples of applications to you to demonstrate the different tuning scenario of KEA. So a little bit background about Cosmos. Cosmos is a big data infrastructure internally at Microsoft. It has around 300,000 servers across multiple data centers. And every day we receive approximately 600,000 jobs from customers. And those jobs are usually submitted in a script with multiple sets of SQL queries pipelined together to be executed in one execution plan. And every year, the total cost of this system is around $480 million. So historically, we have spent a lot of effort to improve the system from the engineering side. For instance, we can improve the workload optimization, the query optimization. We also propose innovative way to reuse the historic work and materialization for the new job instances from historic data. We also develop better testing tool and also better provisioning and scheduling algorithm, etc. But the key question we want to answer today is whether we can use data science and machine learning to further improve this system. And the answer is yes. So the total applications of KEA is actually saving Microsoft more than 60 million per year in COGS. So the presentation today will be organized into these three parts. First, we will introduce the end-to-end methodology of KEA. And then we will dive into the three different types of scenarios that KEA can be applied to. And in total, KEA has supported a set of different applications of Microsoft, but due to the time limit, we will probably just dive into two applications in more detail. So over the years of collaboration, we actually come up with this general template for this type of collaboration between multiple teams, including research, data science, and engineering. So at the very beginning, the first phase is about the fact-finding and system conceptualization, where the domain experts work together with the data science very closely. So the domain expertise will bring in their understanding about the detailed architecture of the system, provide a list of dashboards that they use to monitor the system. They will also grant the access of telemetry data for the data science. And the data science will bring in their understanding about the math, knowledge, the visualization tool, and also the experiment design. And the output of this phase will be a detailed problem definition to tell what is the scale of the project, what are the configurations we want to tune, what is the objective, what are the constraints we need to satisfy. And the second phase is about the modeling and optimization, where we actually develop different methods and models. So what we found in the Cosmos is that usually the configuration that we tune will direct impact some of the performance metrics of the system. And then we can use models to capture the dynamics between different set of performance metrics. And then eventually those set of models can be used in the optimization module to propose what is the optimal configuration we want to try. And in the third phase is actually about the deployment or flighting. So usually before the full cluster deployment, we will conduct multiple rounds of flighting to test or try out this new suggested configuration in the production environment, maybe for a subset of the machines as a safety check. So notice that this full process will be always iterative, so we can keep improving the models and do the changes maybe a little bit more conservatively, step by step. So let's dive in a little bit more into this fact-finding and system conceptualization for this Cosmos system. So one of the biggest challenges we face is here, how we can model the behavior of such a complex system of Cosmos. So on the left-hand side, I'm showing the important elements of Cosmos. So you can see that usually the customer can submit recurrent jobs, for instance, and it's the job template. And each job template will be mapped to multiple job instances. For instance, one at Monday, one at Tuesday. Some of the jobs are daily, hourly, or weekly, or some there can be ad hoc jobs as well. And usually the service level obligation is defined at the job template level that we really don't want to violate this time limit. For instance, the customer say for this daily operation job, we have to finish it within 10 minutes. And this is the agreement we have with our customer. And as many of you might know, for the Hadoop and Yarn system, each job will be decomposed into multiple tasks. And specifically in Cosmos, we are usually looking at hundreds of thousands of tasks per job. And each task will be assigned to a particular node in the cluster. And in the cluster, we can also observe multiple generations of machines that are purchased in different years. So they also behave very differently. So it will become very challenging to model this system, especially considering the job might have significant different characteristics. Some of the jobs are running in seconds, minutes, some of the jobs are running in years. And also the machines have different behavior across different regions, different generations, different model type skills. And also the scheduler will assign the tasks to different machines based on very simple heuristics because of the latency requirement. So we don't really have a good control to say for this job, all the tasks go to this group of machines, so that it is very difficult to develop the model, for instance, at the job level or at the machine level to say for this job, the service agreement is 10 minutes. It is very challenging to develop a detailed simulator to mimic the behavior of the system using one model per machine or one model per job. But after a juristic examination of the system, we actually find out some of the consistency for the task type distribution across different groups of machines. For instance, across different rack, each rack I think is around 40 machines, or across different skills about the machines running from generations to generation. It is actually a similar mixture of different operators or operator type or stage task type across those machines. So we can develop actually the performance metrics at the machine group given this observation. For instance, we can look at what is the task throughput in terms of how many tasks each machine group finished every hour, or what is the total throughput measured in bytes different machine group finished, what is the distribution of resource utilization for CPU, RAM, SSD across different machine groups, and we can develop models to capture those dynamics in a countable number of models. So the three types of applications that KEA can support are the observational tuning, experimental tuning, and the hypothetical tuning. So the operational tuning, meaning that if we can use the existing operation, the existing observational data to predict what the what-if scenario, if we change some of the configuration, we can use this observational tuning. But sometimes we decide it is very difficult to model the future scenarios given just the modeling approach, machine learning. For instance, we change the power consumption completely. It might be very difficult to predict what is the resulting performance change. Then we turn into this last resort, this experimental tuning to actually try out this configuration in some set of the machines in the cluster. And that is the experimental tuning. And the observational tuning and experimental tuning are both focusing on the operational level, meaning that we want to improve the current operation of the system. While the third application type is about the hypothetical tuning, where we are targeting the future operation in some hypothetical scenarios. Therefore, we have to rely on the modeling part. So let's dive into some of the detailed applications so that you will understand the methodology we use a little bit better. So I will discuss the yarn configuration tuning and the skill design a little bit more detail in a minute. So for the power capping, it is the project that we want to decide what is the optimal power provision level for different groups of machines in the cluster, so that we can reach the maximum power consumption harvest, so that we can feed in more machines within the same power switch. And we don't want to impact the performance of the job. If we cap it too high, maybe it will run into the throttling for CPU frequency. And the last application of KEA is about to decide what is the best software configuration. For instance, historically, the logical space of the of the storage is always mapped to SSD or HDD, but we want to know which one is actually the better choice that will give us the best efficiency. Therefore, we can also use KEA using more like an A/B testing type of methodology to tune those configurations. So without further ado, let's dive into some of the application in more detail. So the first one is one of my favorite, is the observational tuning for the yarn configuration. So the parameter we want to tune is called the maximum running container in the yarn init file. So what we have observed in the system is that we actually have multiple groups of machines being purchased in different years, and some of them might be slower and some of them might be faster. So intuitively, if we want to reach a better workload balancing, we want to have more workload on the faster machines, because for each job, the total end-to-end job runtime is usually determined by the slowest task that becomes the straggler of the machine. So if we can have more tasks to be finished on the faster job, in general, the job end-to-end execution time can be improved. However, we don't want to push too much workload on those faster machines because they are faster, because it will result in resource throttling, or there will be more noisy neighbor issues. Therefore, those faster machines might be slowed down because it is overwhelmed. So there can be existing a sweet spot for the workload balancing across those different groups of machines, so we can reach a better workload distribution to maximize the total system processing speed at the cluster level to give us more efficiency. So the detailed tuning approach consists of 2 steps. The first one is about the learning. So in the learning step, we want to better understand the machine response to the configuration change and answer the what-if scenarios using machine learning predictions. So specifically on the left-hand side, I'm showing the data collected by the KEA data pipeline. So every day, the KEAs keep collecting the telemetry data from the cluster, organizing them, combine them, join them, aggregate them to a more understandable format. So this is a figure for the visualization of the output data. So in this scatter plot, we can see the x-axis is showing the average CPU utilization of the machine, and y-axis is the total number of vertices, or the total number of tasks being finished for that machine for one day, and each dot representing one machine. So for instance, you can see if the machine on average is running at 60% CPU utilization for the whole day, it can finish 2,000 tasks. So we can observe a detailed trend for different groups of machines using this visualization. And we can actually use machine learning to mimic the behavior of those parameter metrics. For instance, the total throughput can be a function of what is the total container running on these machines on average, or what is the total latency for different group of machines can be a function of the total CPU utilization as well. So you can see if the machine is running at higher utilization level, in general, the average execution time for each tasks will be longer. So we can develop for each SKU, each group of machine, a set of machine learning models to predict if the machine is running at different utilization level, what will be the total throughput, what will be the latency for the tasks, what will be the resource usage for RAM, SSD, and CPU. And then those models will be input to the optimization to suggest the optimal configuration change. So for instance, after multiple rounds of discussion with the product team and the PM team, we decide we want to actually make more money from the system, meaning that we want to extract as much as possible the usable capacity while maintaining the same level of performance as now. So imagine that if we can better balance the workload distribution, we might reach a better state that all the jobs runs faster, but we want to, in this case, inject more workload to the cluster such that we bring back the performance to the same level as now, but we can process more capacity and sell it to the customers. So we want to maximize the total containers can be run simultaneously in the cluster, which is the token that we sell. And we want to subject to the same level of performance measured by the average vertex execution time. We want to subject to the resource constraint for each machine. It is within the total limit it is currently equipped with. So on the left-hand side, I'm showing the suggestion of KEA for different generations of machines. And the blue bar is showing the current number of total average containers running for the Gen 1.1 machine. And the orange bar is showing what is the optimal level the model think it should reach as the number of containers on average to run on this machine. So we can clearly see that for some of the faster machines, usually Gen 4, we are suggesting to run more workload, while for some of the slower machines, KEA is suggesting to run less. And it actually gives us a detailed quantitative measurement to say what are exactly the numbers we want to change for this particular set of configurations. And we conduct multiple rounds of flighting in various clusters to validate whether this change can give us better throughput, better latency, and eventually now this configuration change has deployed full clustered for all the 5 clusters of Cosmos. And we also evaluate this performance change using treatment effects, for instance, in these 2 figures, to measure whether we can statistically consistently beat the behavior or beat the performance we have before this configuration change. And eventually this project is resulting approximately 18 million per year worth of improvement in COGS. So the implication of this project is that these what-if scenarios can also be extended to other parameters. For instance, if we want to tune the maximum queuing learns for different groups of machines, we can also develop different similar methodology to mimic what is the distribution of queuing learns, how it will impact the queuing latency across different groups of machines. And especially we usually can see for slower machines, the queuing latency is longer and also the queuing learns is long, so that we can tune it differently so that we can reach a better balance. So the second application of KEA I want to discuss is about the hypothetical tuning for the skew design. So what we know for the new generation of machine is that all the machines will have 128 cores. But the thing we don't know is what is the optimal number, what is the amount of SSD or RAM we should purchase for this group of machines. Therefore, we want to also leverage KEA, leverage the current telemetry data to predict the future. So on the left-hand side, I'm showing the resource utilization for the Gen 4 machines in the cluster for the SSD and RAM. So you can see the x-axis is showing the CPU utilization of the machine as a snapshot, and the y-axis is showing the SSD or the memory use as a function of the CPU utilization. So you can kind of see the trend that if the machine is used heavily, the SSD usage or the RAM usage will be higher. And specifically for this group of machines, if it is running at 100% CPU utilization, that means it is using all the 40 cores. So in the future, we want to have 128 cores. So actually, it is a projection of this curve all the way to 128 cores. And then we can use this current observation for the resource usage, develop models, and predict what is the usage we will have for the new machines with more cores. And specifically, we can also take into account the statistic, the noises, the variation of this uncertainty into the model. So in the paper, we discuss how to use Markov chain Monte Carlo simulation to estimate what is the total cost of the machine if we buy it with different amount of RAM and SSD. So you can imagine that if we buy too much RAM or too much SSD, the majority of the time, they will just stay there being idle. And we are always struggle to get more CPU cores because we have so much resources to be idle that is not cost efficient. Or if we buy too little amount of RAM or SSD, we will always run into out of memory issue, resulting in job failures. So that also come with some penalty. So there's some sweet spot there as well that we can minimize this normalized cost to consider the various penalty. And this is the optimal configuration we want to move forward with to buy with the new SKU. So in conclusion, KEA is a very flexible configuration tuning solution that supports both the operational applications and planning level applications. We monitor the cluster performance and collect the telemetry data on a daily basis. We model the machine and cluster behavior using machine learning algorithms, statistic algorithm, and propose the better configuration using optimization or heuristics. And we also design experiments for A/B testing or the flighting tool to do a safety check before the full deployment of the cluster. So in total, we can reduce the costs with very minor code change to the original system to achieve better efficiency. So this concludes my presentation. I'll be opening up for any questions. Thank you.